Happy day and welcome everybody. We're talking titration curves today. Okay, so let's first just really briefly review what is a titration. What is happening during a titration? So typically what you'll have is you'll have usually a base you put in your burette, and then you can have your acid that is inside of your flask. And in this case, they chose hydrochloric acid and potassium hydroxide, 2 strongs. And then we also need to make sure that we select an indicator too. So usually if it's a strong acid, strong base, phenolphthalein changes around 8.2, which on your curve, even though we know that a strong acid, strong base should give us a pH of about 7, that long kind of change that happens as soon as it's neutralized, where the pH changes from like 4 to 10 generally, and 8.2 falls in there. And so that's perfectly fine. Here they just have it's on a stir, so it's just kind of stirring. Normally what you would need to do is kind of like just keep either moving your flask around, or you can put a magnetic stir on the inside there, okay? And so then what you'll do is you'll start titrating, and you really want to make sure that you slow down. So let me kind of fast forward this here a little bit. And so you want to go to dropwise. Now, if you do wait a second, you'll see a little bit of pink come in. And so what's happening there is that when you drop the base, sometimes the base is looking for acid. The base always wants to react with acid to neutralize, right? To make water and salt. But sometimes it actually will find the indicator first, and then it's like, ooh, found some acid, hold on, let go of that, and then go back to with the acid, and so then it goes back to clear again. So it's not until all of the acid is gone and neutralized, and that's when your solution will actually turn pink and then stay this like kind of bright like purplish pink color, okay? Now once you have this, then you know the molarity of your acid. We knew that to start, so we knew what we put inside of here. And we knew the volume, original volume of our acid, so MAVA, so you're not changing that. Then we also need our Mervet. And so the molarity of the base is what I'm looking for, and then I've got the volume of my base, this 19.04, and then you work out your calculation. Now, you can also do this for a weak acid and a strong base, and everything would end up coming out the same exact way, okay? The only difference is going to be your titration curve is going to look different. So we're going to take a look at some titration curves in just a little bit here. The other thing that I wanted to make sure that I reminded you of is if you select your acid and your base, and you select one that is maybe your acid is diprotic, or maybe your base, you've got 2 hydroxides, for example, like CaOH2. Well, if that's the situation, don't forget, when you go to calculate MAVA equals Mervet, you have to use that ratio in your calculation. So either do stoichiometry, or you use the ratio where if it's CaOH2, then my Mervet side, I would multiply by 2 when I go to do the algebra. Okay, so just kind of a reminder on that piece. All right, so let's take a look at the notes here. Okay, so we know what a titration is. And so you usually have your burette, the one solution that they call the titrant. And so then you end up titrating it, and you get this graph that looks something like this, okay? If it's a strong acid, strong base, this is pretty much the graph that you're going to get. So your pH, you're starting with an acid inside of your flask here in this situation. It's going to remain constant. And then you get that shooting up, and you can see that right at 50 mils dropped, you get this shooting up from a pH of 4 all the way to a pH of 10, okay? Now, this is where you would stop. Anything that is happening after this point here, is actually an over-titration, okay? So this is over-titrating anything after this point, okay? And so, so normally you would stop there, but it is nice to kind of get this curve, and so that's how you would get that. But in this situation now, you would assume that all of your acid is gone, has completely reacted, and you just have your base and your indicator, for example, inside of there, okay? The water and the salt, right? And so let's take a look down here. And now we already talked about a problem where, what if you have equal acid and base concentrations at equal volumes? Well, then what should the pH be once it's neutralized? Well, it should be 7, okay? So that makes sense. But then this question says, what if you haven't actually reached the neutralization point and you've only added 49 mils of base, but you have 50 mils of acid? Well, you're essentially right here, and if we draw a line going up from 49, and then I come across, it's actually looking something more like a pH of 3, okay? So a lot of times it'll be a multiple choice problem. They'll give you options for pH, and they're usually not even that close to each other. So they give you 4 like answers that are separate from each other. So if we worked out the calculation, we would see, and I like to do this in 4 steps. So the first step, I use Mervet equals Mervet, just normal Mervet equals Mervet, except I want to see what the moles of each one are. That way I can imagine they're reacting, okay? And which one's going to be completely gone? Well, this 0.00490 moles of NaOH should be completely gone and used up because I have less of it. So how much of the H plus or HCl reacted? Well, 0.00490 because they're going to be equal amounts that react. So I'm getting 0.00010 after I subtract. So that's step 2, is figure out how much you have excess. Step 3 is, what's my new molarity of my acid? Because when you go to calculate pH, this is in molarity, not moles. So I take my moles that I figured out here and divide by my total volume. Okay, so you want to make sure you're adding your 2 volumes together. That gives me my new molarity. You simply negative log it, and that gives you what your pH is. Okay, so now let's take a look at a few different graphs here. And I want to compare the strong to the weak. So what happens if you're adding a weak acid? Okay, so it says there are 3 major differences between the curves. So one is the weaker acid has an initial higher pH. At the beginning, the pH rises more rapidly because if you have a strong base, then it's almost like a shock to it, right? So it's going to kind of shock it a little bit, but then it's less rapidly. So if we see here, notice that this strong acid line is a lot more, just more of a plateau, whereas on the weak, you kind of get this a little bit more of a curve in the beginning, okay? So that's very indicative that you have a buffer also that's made. So I'm going to come back to that in just a second. And at that point, then your pH should be greater than 7 when you're at your equivalence point if you're starting with a weak acid, okay? So point of emphasis, for a strong acid, weak base, we said the pH changes rapidly at the beginning and then has a gradual slope near the equivalence point if it's weak. So if you have a weak acid, strong base titration, then this is what we were talking about here, okay? Now, the other thing is to really keep in mind is that gradual slope, why does it happen? Well, it happens because you've actually created a buffer solution. What is a buffer? Well, a buffer can be defined either as a weak acid and its conjugate base or its salt, or a weak base and its conjugate acid. So what we have is we have a weak acid and its conjugate base. So if you have your weak acid plus, as soon as you start reacting it, the conjugate base starts forming, okay? And so that's basically acting as a buffer. So an important point in this graph is actually what happens halfway to the equivalence point, okay? The halfway mark to the equivalence point is where your acid concentration, so right here, your acid concentration is equal to your conjugate base concentration. What's the importance of that? Well, the importance is if we use Henderson-Hasselbox equation, pH equals pKa plus log of Cb over A. If your conjugate base and your acid are the same and you divide them, the concentrations are the same, you get log of 1. And the log of 1 is equal to 0. So what happens is your pH is then equal to your pKa, okay? So this halfway to equivalence point is really important when we're dealing with AP questions, okay? So keep that one in mind. This is doing the reverse. This is if you had a weak base, so starting at a pH of 11 instead of 13 with your strong base. And so again, you kind of get that little dip that happens there. Again, indicative that you have a weak base, okay? And now look at your equivalence point. Your equivalence point should be less than 7 now if you have a strong acid, but you're starting with a weak base inside of your flask. Okay. Polyprotics, real quick on polyprotics, that means that there are multiple ionizable hydrogens. And so what happens here is we can see that we've got an equivalence point there and an equivalence point there. This must be triprotic, where I've got 3 equivalence points, okay? And so that's basically it, just kind of giving you an idea of how that works. Happy day, everybody.